All right, I want to get you thinking about two things, balls that are going down differently shaped ramps, and then I also want to get you to think about pendulums. And the math for how you get to equations and pendulums is kind of handy. It's going to come up later in the year as well. So hopefully you get a handle on that. So first thing I want to look at is balls on a ramp. So in this case, I have I have three different flat surfaces. So each of these balls, A, B, and C, is starting with the same velocity. But notice what's going to happen. So in the A situation, so my velocity is going to remain constant all the way across. So we'll get this for a matter of time. But notice what happens in B. So whenever this ball drops below this level where it is, it's going to gain kinetic energy. So the entire time that it's down in this dip, it's going to be going faster. And then it gets back up to B, and it will return to that same level of kinetic energy and the same velocity. But notice what happens. So it had a period of time where it was going faster. So ball in B will get to the end point with the same velocity, but it'll get there faster. Similarly in C, the ball in C is going to spend a longer time with more kinetic energy. So it's going to be going faster, and it will get to the end point even faster. So we'll look at the same thing on a ramp. So this is a little video that shows 4 different ramps, and see if you can make out what happens to the balls and predict which one's going to get to the bottom first. So I have red, blue, yellow, and green ramp here. Hopefully you can make out the different shapes. So make an estimate. Which one do you think is going to get there first? Which one's going to get there last? Okay, let's see what happens. Okay, so hopefully you saw that the ball that went down the, let me go back to the beginning here. So let me get to the end. Okay, so notice the shapes on these ramps, right? So the ball that got to the ramp, got there last, is easiest to make out in this picture, right? So this is the red one. So he's going slower for a longer period of time and then gets to the end. The one that was the fastest was the one of this blue ramp. So it accelerated more quickly at the beginning, and then stayed at that higher rate of speed for this last bit along the bottom of the ramp. And yellow and green were intermediate to that. Right? So hopefully this makes sense to you. So at the end, all of those are going to get to the ramp at the same velocity, right? So the amount of energy that's involved is still the same. They'll get there, if they're the same balls, they'll get there with at the same velocity, but they'll get there at different times. So we'll be able to see which ones accelerate the fastest and which ones get to a higher velocity more quickly. Let's switch to pendulums. So pendulums we also think about in terms of energy. So I can think of energy of a pendulum coming from gravitational potential energy being converted to kinetic energy. So it's going to have maximum gravitational potential energy when it's highest, right? It doesn't matter how far it goes left to right. What matters is how high it is in the gravitational field. So how far away is it from the surface of the Earth? And it's going to be going fastest when it's right at the sort of equilibrium or the lowest point. So this is something that we can look at in terms of energy, but we have to be careful about it. And there's a little trick that we do to make sense out of this. So let me draw a little bit of math to help you understand what's going on here. So let me switch to, stop. That's right. Okay, so a little bit of math on pendulum. So here's my pendulum. Right? I'm going to think about, it's going to be at the lowest position here. And that's where it's going to have the maximum velocity. So that's going to be all kinetic energy. And when it swings up to the top here, this is where it's going to be all gravitational potential energy. And I can do this, right? I can say, well, my gravitational potential energy is going to be equal to my kinetic energy. Right? And how do I get gravitational energy? Well, I need to know how high it gets, right? So the trick with this is what I'm trying to find is what is the height in here, right? So the only thing I care about is the vertical distance. Well, I can do a little bit of a trick. So I know it has some length here, and when it's down here, it's going to have the same length, right? The string isn't changing in its overall length. So usually how this goes is that I have some angle that I push it out to, and then I let it go, and I can figure out how much potential energy there is involved with that, and I can also figure out what the velocity is if I just know that angle. So here's how I'm going to think about this, right? So I'm going to see if I can find this distance in here using a triangle, right? So this is a right triangle. If I know an angle and a hypotenuse, I can find this distance. And my height will then be the difference between my total length of my string and that distance for that leg of the triangle when it's up in the air. So let's do a little bit of math and see what this looks like. So I'm going to say, well, my distance, right, this is my leg that's adjacent to this. So it's going to be hypotenuse times the cosine of the angle. And now my height that I'm interested in is going to equal my total length minus my distance, which is L cosine theta. And a lot of times we'll write this as a simplified form. I can factor out L in that. So now I can go to my energy equation and we'll get something that that's a little bit convenient. But this is the key part of it. This is the key part of it, that the only thing I care about is the vertical height, and I can get to that vertical height by using the length of the string twice, right? The length of the string when it's way out, and the length of the string when it's perfectly horizontal. So we can finish this. So I say, since we're close to the surface of the Earth, I'm going to say this is mgh, and I'll set that equal to 1/2 mv squared. I'm interested in velocity here. Notice I don't have springs, so my mass is going to cancel. So I can say v is going to be the square root of 2gh. And now I'll plug in what I had for h. So this is going to be square root of 2g times L times 1 minus cosine theta. Really not worth memorizing the formula, but the thing that is helpful to remember is how we got to this. So I'm using the angle to help me figure out this leg that I need to subtract to find the height. Anyway, I hope that's helpful, and we'll talk to you soon. Bye.